Hello there, Smart Coder. How's it going? Have you done the daily already? Now I should stop watching. Yeah, you can watch the video later. The bot. I'm gonna go over the daily first, um, and then I'm gonna explain another problem, which is also about the games. But I don't know, as you wish. As you wish. I don't want to spoil it for you. Anyways, I'm gonna start. Let me share the link. So this is today's daily. Predict the winner. You're given an integer array, nums. Two players are playing a game with this array, player 1 and player 2. Player 1 and player 2 take turns, with player 1 starting first, as you would expect. Both players start the game with a score of 0. Each turn, the player takes one of the numbers from either end of the array, reduces the size of the array by 1. Player adds the chosen number to their score. The game ends when there are no more elements in the array. Return true if player 1 can win the game. If the scores of both players are equal, then player 1 is still the winner, and you should also return true. This is important. It's kind of an odd rule that ties go in favor of player 1, but we gotta do what the statement says. And you may assume that both players are playing optimally. We have a few examples, and so this is important here in this problem. The maximum number of elements is 20, and the numbers themselves, the values are quite big, 10 to the 7. So this is a hint that whenever you see a smaller number to around 20 or less, you can start considering all subsets. So one thing to note is that here the players choose elements from the ends of the current interval. So that means that we could characterize the remaining numbers by just maintaining the ends of the interval, which initially are 0 and n minus 1. But the thing is that we need to, the fact that it's 20, first contest, not really. I created the account for the channel, and I want to compete with my channel account, so don't worry about it. Thank you. Okay. So Yes, my idea is, taking into account that there are only 20 elements, is that we can use bitmask.dp to remember which elements each player chose, so that then we can compute, once we make all the decisions, we can know which player won, without keeping track of the scores, which can be pretty big. So the idea is to do some recursion where this recursive function is going to tell us whether the current player wins or not. And just for convenience, so like I said, I'm gonna keep track of the ends of the interval, I and j inclusive, and I'm also going to keep track of the elements that each player chose. So this is just for convenience. We don't need to keep track of both separately, because we know that if one of the players did not choose an element, then the other player chose it, and so on. So this is a redundant parameter, but for convenience, I think it can make sense. So first and second are going to be the number selected by the current player, the player that plays first at this point of the game, and second is going to be the other player. Okay. So what is our base case? The base case is going to be, since this interval is inclusive, if I is less than or equal to j, we still have elements to choose. But if a is greater than j, then we're done. And in that case, we are going to compute the score of a player. Let's say that this is the chosen elements mask. So the score is going to be if the ith element is in chosen, then we want to add it. So that is going to be the score of the player with the chosen. So like we said, we define wins as whether the first player in the current state wins. So that means that we need to compute the score of the first player, score, and we want to know if it's greater. We don't need to. We can have like the total. And we want to know if it's more than half, but to avoid dividing, we can multiply by 2. So 2 times the score has to be greater than or equal to total. But there is some, this is not exactly true, because we have to take into account the tie-breaking rule. But let's leave it at that for now. So then what we want to do is to, as usual in this kind of games, we want to call recursively. We have 2 options. We can choose the ith element or the jth element. Okay, so that means that we win. We're going to choose the option that makes us win, and that means that we win if for one of the option our opponent does not win. Okay, so this is the Boolean expression for this condition, and we want, so now we want to know if our opponent wins. So that means that the first is going to be the second, and the first, in this case, we are going to choose the ith element. So we mark it and we increase the ith end. We keep j equal, or we are going to choose the jth element, in which case we decrement j by 1. So those are our two options, and that is pretty much it. So initially none of the players have selected anything, any numbers, and the interval is the whole array. And this is pretty much it. It's pretty much a one-liner or two, however you want to count it. But remember that we're not doing the tie breaks, so now we'll have to fix it. But let's see if it passes the example. It does. And let's think about the tie break. Yeah, this is a little tricky with this way. I mean, this simplifies the code because you are changing perspective depending on the depth of your recursion, because you're alternating between the first and the second player. But the problem is that the condition for winning changes depending if you are the overall first player or the overall second player. Okay, so when we are computing this, depending on the parity of the amount of numbers that we have, for example, if there is only one number, if it's odd, then the first player is going to choose the first number, and then it's going to be the turn of the second player, and in that case we're gonna get this condition. So when n is odd, at this point we're going to be the second player. Okay, so we want to know what is the minimum. So we said that if it is odd, we are going to be, well, let's say if it is even, we're going to be the first player when we get to the final condition. So we want to know if the first player wins. And in that case, the double score has to be total at the minimum. But if we are the overall second player, then we need more. It's not enough to get half of the score. We need to exceed that. So we add 1. And here, this is the minimum double score. And this is it. And it passes. And we completed the daily. Pretty easy. So yes, I think this problem is a little tricky because usually 20 having the number of states that you have here might be a little too high. Yeah, I would have to think about how many states can you have all the. Yeah, I guess you can have any of the subsets. So if this is 2 to the 20, like a million, times 20 squared, that might be too much. But I mean, when you get this kind of small numbers, it makes sense to maybe try out this kind of solution and see if it's good enough, and otherwise try to think of something clever. But it's very rare that you can solve a problem, you can find some winning strategy, and if you can find a winning strategy that does not need to try all possibilities like this one, this number would be higher. So that is a hint. I mean, of course, sometimes I guess they could throw you off by choosing some numbers maliciously, but will an interviewer tell you the parameter size is so small in an interview? Well, usually in interviews you get like a vague, I mean, of course it depends, but in many cases you get like a vague problem statement, because the interviewer expects you to ask good questions to clarify, and maybe the interviewer wants you to actually consider different constraints and maybe talk briefly about what you would do with different constraints. And I guess eventually they tell you what you can assume when you're asked to implement a solution. So eventually you are going to know what the constraints are. I mean, you need to know to make a decision. But my point is that might be useful to know how to think about the trade-offs for different constraints. So today I looked into this problem, which is similar. I mean, well, it's a game, and like you can guess by the title of the stream that you can solve it by DP. So they tell you that in the 100 game, two players take turns adding to a running total any integer from 1 to 10 inclusive. The player who first causes the running total to reach or exceed 100 wins. What if we change the game so that players cannot reuse integers? For example, two players might take turns drawing from a common pool of numbers from 1 to 15 without replacement until they reach a total of 100. Given two integers, maths, choosable integer, and desired total, return true if the first player can force a win. Otherwise, return false. Assume both players play optimally. So let me first explain. I mean, it's not necessary for this game, but might be interesting. This 100 game. So like it says there, this is a famous mathematical game where, well, like it says there, two players alternate, they add up to a running total, a number between 1 and 10 inclusive, and whoever exceeds 100 gets to 100 or more wins. So one way to think about these problems is by doing, you can think about it backwards, right? Because let's say you want to reach 100 or more, right? But let's say that the running total when it's your turn is 90 or 91 or so on up to 99. Then for any of those values you can always get to 100, so you can always win, right? I mean, if you can choose 10 if you're at 90 and you get to 100, and here you choose 9 and so on, or and up to 1. So that means that any of these positions are winning. Let's say that the winning positions are blue, so all of these positions are winning, okay? And we can say that this is losing in a sense. I mean, the game ends, but if it is your turn and you are at 100, then you lost. That's a way of thinking about it. But what happens if you're at 89? Then it is the opposite, because no matter what you do, if you add 1 or if you add 10, your opponent will be in a winning position. So that means that you will lose if your opponent plays optimally. So that means that 89 is losing. So this is losing. And then you can see that the pattern repeats, because again, if you are at a distance of 10 or less to a losing position, you can choose a number that gets your opponent to a losing position, so all those positions are winning. So at every point the losing positions, the initial is 100, then you subtract 11, you get to 89, then you get to 78, and so on. And eventually you'll go, since this is subtracted 11, you get to 1 if you subtract 99. 9 times 11. So that means that if you start, that means that 1 is a losing position. So if you start at 1, the first player will lose. So this is a game. I don't know if there's maybe there is a problem in, I think there is a problem in LeetCode about that game. But now you can forget about that game, because in this variant of the game, it's not that simple. I mean, in the other case, it was pretty regular, because we could, it was clear, it was clear what numbers we could choose at every step, at every turn. But here, since we are not replacing the numbers, it's not easy to know which numbers are available and what you're going to do at every position. So in a sense, you can think about like the state of the game is a lot more complicated, or because it depends on the numbers that you have available at that point. In the previous game, the state of the game was only the running total, but here it is more complicated. But we can, sometimes we programmers can solve these more complicated problems without thinking too much, without finding a winning strategy, and just trying all the possibilities. And that's exactly what we're gonna do. Again, here the numbers are pretty small, which hints to some kind of DP solution, bit mask DP, because again, since we are choosing numbers, so what is this idea of DP with a bit mask? The problem here in this kind of problems is that you are making decisions, you are choosing numbers without any restriction in any order. So that means that in some sense you need to remember the choices that you made. So you need to remember all the subsets of numbers that you could have chosen. And in other problems you are making decisions in some order. So you only need to remember what suffix of an array is still you need to make decisions for. So again, we are going to do a recursive solution, memoization, which is very simple in Python. And this is going to tell us if the current player wins. And we want to know if like I said, this is going to tell us, this is going to be a bit mask, which is just a subset. You have to demystify the bit masks. It's just a way to represent a subset. And this is going to indicate which numbers we have used already. And then this is going to be the desired total that we are going to have it as an argument here, because we are going to be changing it. We're going to subtract the numbers that we choose, and we are going to be changing it. So what is the base case? If we have achieved the desired total, which is it's 0 or less, then we lost. Okay, it means that our opponent exceeded, reached the total or exceeded it, so now it's our turn, we have lost. And then otherwise we are going to try all the numbers from 1 to the max choosable integers, well, inclusive, so it's +1 in Python. And we want to know if it is not used. Okay, so that means that when we end the ith bit of the mask with the mask used, we're going to get a 0 if that bit is not set, which means that we have not used that value. And we're going to call recursively. We want to mark that the ith element as used, and we want to subtract that value from the desired total. But here's the interesting part, which is the same that we did in the previous problem, which is that we win if in any of our choices our opponent does not win, which means he loses, or he or she they lose. So this is pretty nice in Python, that you can write this kind of expressions very concisely, and it's pretty similar to how we think, how we say these things and how we think about them. So yes, if for any choice that I can make my opponent loses, then of course I'm gonna make that choice. That's what playing optimally means, and that means that I can win. If I play optimally, I win. So that's it. Pretty simple, no? And initially we haven't used any element, and the desired total is the desired total, the initial. And this is it. But yeah, there are a few edge cases in this problem. I think that's why this problem has a very low acceptance rate. I mean, relatively low, because for example, there are a couple of counterintuitive cases. Like, you can get a desired total of 0, and in that case the first player wins, which is kind of it's kind of arguable. If we got a wrong answer, because our solution, when we get to 0, we lose. But whatever they say, we can, if they define, I think it would make more sense to not have that desired total, because you already achieved that total, so it's kind of trivial. But yeah, I think we have to handle that separately, and they want us to return true. In that case, fine, whatever. But then there's another edge case, which is they don't guarantee that the desired total is reachable. Okay, maybe after choosing all the numbers you don't get to the total, and that's kind of weird, because yeah, in that case, like, nobody wins, but technically you have to say that the first player does not win. Okay, so again, we want to handle that separately. And what is the total sum that you can get? This is going to be the sum of all the numbers from 1, 2 until max choosable integer, which is this expression, which is very useful. And if this is below, we cannot reach the desired total, then the first player does not win. Again, that's kind of a controversial case. Hey, Lucia. And we got it. We got it. Accepted, and it beats 90% of the users with Python 3. Oh, so one interesting thing to notice here, very interesting, is that, so what is the number of subproblems of this solution? So you might be tempted to say that it's on the one hand you have all the subsets of 20 elements. That's 2 to the 20, which is, I mean, about a million, a mega. And then, well, desired total can be from anywhere from 300 up to 0 or even more, because it could be negative. But notice that the subset already determines the desired total, because the desired total, the argument is going to be the initial desired total minus all the numbers that have been marked as used, that have been used. So that means that this is a redundant parameter. We have it just for convenience, but the number of subproblems is really 2 to the 20, so about a million, which is usually good enough for LeetCode. And then in terms of transitions, we have the max choosable. We have to go over all the numbers from 1 to max choosable inclusive. So in total, the number of iterations of our algorithm is 300 million. I mean, that's a little high. Oh, no, it's not 300. No, that's the desired total. No, the max choosable integer is up to 20. Yes, I was I was surprised. No, it's 20 million. That's okay. 300 millions would be maybe over the limit. So, yep, that's it. We learned how to solve games with DP. It's a very useful technique. This is a very cool idea. This recursion to solve games. I mean, this is essentially what it's done to make optimal players of any games like chess, tic-tac-toe, whatever. It's the same logic. You consider all your possible moves, and you call recursively from the perspective of your opponent, and you choose the you choose the option that maximizes your score, which is the option that minimizes your opponent's score. That's why this is called min-max. So it's the same principle. Could come up in interviews. I used to ask a question about how would you program an optimal tic-tac-toe player in interviews. So yes, it's pretty possible to get these kind of questions. So it's good to know it. All right, so yeah, I guess that's it for today. We also in addition to, we got a little math lesson with this problem. This concept of winning positions and losing positions and thinking backwards about a game. and alternating, trying to put your opponent in a losing position, forcing your opponent to put you in a winning position. So yeah, I think it was a good one. So thanks for watching and see you in the next one. Bye bye.